So good morning and good afternoon and good evening for everyone. We have, I think we are covering 7 time zones in this defense. So I thank you. I thank all the committee members, Vladimir, Ian, which are early in the morning, and Eve, who is working in the evening of his vacation, of his summer vacation. So I thank you for arranging the time to participate in Clarice's defense. And also thank my colleagues Monica and Paulo for participating in the defense of the doctor's thesis of Clarice de Amorim. The work was advised by myself and Dr. Haniana Ponce. Then Clarice is gonna make the presentation that's gonna be followed by questions from the committee members. So Clarice, you have around 40 minutes to present your work. Good luck and thank you very much.
Thank you, Professor. Good afternoon, everyone. My name is Clarice de Amorim, and today I'll be presenting my PhD thesis titled Core-Scale Mechanisms of Oil Displacement by Emulsion Injection. This work was conducted under the supervision of my advisor, Professor Márcio Carvalho, and my co-advisor, Dr. Haniana Ponce. I would like to start by thanking the committee members for accepting the invitation to participate in my examination. I also appreciate the presence of everyone here today. Water flooding remains the prevailing method for extending the productive life of oil reservoirs. However, the high mobility ratio between the injected aqueous phase and the displaced oil phase drives the flow through preferential flow paths. In natural resources, this imbalance in mobility is strongly influenced by the heterogeneities of the formation. At the core scale, water navigates through flow paths with lower capillary resistance, leaving significant amounts of trapped oil behind. To address this limitation, core blocking agents have been studied to reduce water mobility in hypermobility channels. Among these agents, oil in water emulsions have proven especially effective in decreasing water mobility, resulting in a more favorable displacement front. Emulsion injection involves the trapping of droplets within porous media, reducing the effective permeability of the displacing aqueous phase. As illustrated in the following sequence, during water flooding, water flows through hypermobility paths where capillary resistance is lower, leaving behind trapped oil. When emulsion is injected, the dispersed phase navigates these preferential paths, restricting the flow as the droplets become trapped. During subsequent water injection, the water is redirected to previously unswept regions of the reservoir, mobilizing trapped oil. Microfluidics is the science of manipulating small amounts of fluid. Model porous media devices are usually made from transparent materials and are molded to create a network of pores and channels that mimic the geometry and connectivity of real porous media. They allow precise control over pore structure parameters, surface wettability, and flow geometry. When combined with pressure drop and flow measurements, macromodels offer a detailed correlation between macroscopic transport properties and macroscale displacement mechanisms. Fluid flow in macrofluidic devices is quite different from that in larger systems. The channels in these devices are only tens to hundreds of micrometers wide, which gives a high surface area relative to the fluid volume. As a result, surface forces like capillary pressure, interfacial tension, and wettability dominate the flow. These effects cause the flow to deviate from what we would expect based in larger systems. This video illustrates the displacement of 2 immiscible fluids. The non-wetting phase, dyed in blue, is displacing the wetting phase, dyed in yellow. At slow displacements, capillary forces dictate how the fluids are displaced and their arrangement within the medium. Interfacial tension is the force that acts to minimize the energy at the interface between both phases. This force causes the interface to curve, creating a pressure difference known as the capillary pressure. In equilibrium, this pressure difference is maintained by the interfacial tension. Wettability is the tendency of a liquid to spread on a solid surface when another fluid is present. It has a significant impact on capillary forces and fluid flow behavior. Both forces drive the flow at the pore scale. Immiscible displacement is usually characterized by the capillary number, which is the ratio between the capillary and viscous forces. Emotions are two-phase systems consisting of immiscible fluids, where one liquid is dispersed as small droplets within another liquid. This image shows oil droplets dispersed in a continuous aqueous phase. Emulsion formation is achieved by homogenizing the oil and aqueous phases in the presence of a surfactant. Surfactants are amphiphilic molecules with a hydrophilic head and a hydrophobic tail. At the oil-water interface, the hydrophilic head embeds into the aqueous phase, while the hydrophobic tail extends into the oil phase. Emulsions are thermodynamically unstable due to the additional energy at the interface, leading the phases to separate over time. Surfactant molecules adsorb to the interface, forming a protective film. Kinetic stability stems from this protective film, which prevents the phases from separating over time. Interfacial films act as a physical barrier against drop coalescence. When two drops attempt to merge, this film needs to first drain and then rupture. Surfactants slow down the drainage by extending to the bulk phase, which prevents droplets from approaching each other and merging. Describing the transport of droplets through individual constrictions involves complex interactions between drop deformation and capillary forces. When emulsion droplets flow through porous media, drops larger than the pore constrictions can either become trapped or squeezed through the narrow gap, depending on their ability to deform. This deformability is influenced by emulsion properties such as drop size and interfacial tension. Retention events occur when the capillary pressure at the pore constriction exceeds the viscous pressure driving the flow. When the viscous pressure overcomes the capillary pressure threshold, the droplet deforms sufficiently to flow through the constriction. Emulsion plugging occurs when droplets of the dispersed phase become trapped in pore throats as they flow through porous media. As the droplet enters the throat region, strong capillary forces arise due to the reduction in the radius of curvature at the droplet's tip, a phenomenon known as the jamming effect. This capillary resistance is described by the Young-Laplace equation and is a function of the interfacial tension and the droplet capture radii. This video demonstrates a drop being trapped at the constriction by capillary forces. To overcome this resistance and flow through the pore constrictions, additional pressure is required, which can be achieved by increasing the pressure gradient. Now I'll talk about some works conducted on emulsion flow in porous media. Macauliffe was the first researcher to report a water flooding field test using crude oil in water emulsion as plugging agent. His study demonstrated that emulsion injection enhanced oil production and improved the flooding pattern by mitigating water channeling. Building on this, So and Radke further observed that emulsion flow resembles a filtration process. They found that larger drops are captured by smaller constrictions during straining, while smaller drops are retained on surfaces through physical forces in a mechanism known as interception. Copes and collaborators demonstrated that the mobility reduction of water is strongly dependent on the capillary number and the drop size. They identified a critical capillary number below which the mobility reduction factor decreases significantly. Oil displacement tests using oil and water emulsions were further investigated by Gillen and collaborators. They examined the effect of the capillary number on curve flooding test and the mobilization of residual oil in porous media macromodels. The use of macromodels has been increasingly adopted to visualize pore-scale events during the transport of emulsions. As Izov focused on examining droplet retention events, Gillen conducted oil displacement tests by alternating between water and emulsion injections Spears investigated the transport of emotions in both linear and radial flows, as well as the effects of the wettability on emotion flow behavior. Numerous studies have explored the effect of the drop size in respect to the pore throat diameter on the trapping of droplets. The consensus in the literature is that drops larger than the pore throats are more likely to plug pore constrictions. The ability of large drops to overcome capillary forces and pass through a constriction depends on the capillary number. Generally, it is agreed that higher flow rates lead to increased droplet mobility. Capillary resistance is further influenced by oil and water interfacial tension. It has been established that interfacial tension affects both the depth of emotion penetration into a porous medium and the effectiveness of droplets in plugging pores. Finally, the flow resistance is significantly influenced by the number of droplets flowing through porous medium. So despite significant progress in exploring emotion injection as an enhanced oil recovery method, much of the existing analysis has predominantly focused on characterizing drop retention and mobility reduction through pressure difference data from core flooding experiments. Visualization techniques have provided valuable insights into the oil displacement process during emotion injection. However, a comprehensive understanding of pore-scale flow dynamics is still lacking. The effect of the capillary number on mobility reduction, especially in radial flow conditions where velocity varies with radius, requires further investigation. Gaining a deeper understanding of this relationship is crucial for optimizing pore blocking strategies and improving the efficiency of oil recovery. So the main object of this work is to relate the water phase mobility to the capillary number and the emotion drop size. This study aims to enhance the understanding of pore-scale mechanisms governing flow in porous media using a macrofluidic approach. By elucidating the relationship between the capillary number and the emotion drop size on mobility reduction, the findings can contribute to effective design of emotion injection to enhance oil recovery. The experimental work includes the microfabrication of model porous media devices, formulation and preparation of a stable polydispersed oil and water emulsion, and the assembly of a macrofluidic experimental setup to assess emotion injection in single and two-phase flows. So two-dimensional macromodels were used to investigate pore blocking mechanisms caused by emotion drops. The devices were designed in two different geometries to enable the study of both linear and radial flows. The devices were fabricated from PDMS using soft lithography technique. The porous media is composed of a structured network featuring both straight and constricted channels. Constrictions are randomly placed within a regular grid of evenly spaced square posts, forming a square-shaped unit cell. The channels have a square cross-sectional profile, with both depth and width measuring 100 micrometers. The constrictions within these channels have widths of 45 and 75 micrometers. The posts themselves measure approximately 200 by 200 micrometers square, excluding the protrusions. This study focused on the injection of a dilute and stable oil and water emulsion. Oil drops are dispersed in a carrier phase of surfactant solution. Sodium dodecyl sulfate was used as the surfactant. To enhance visualization and distinguish between phases during the flow tests, fluorescent dyes were added as the fluids themselves are transparent. Emulsions were prepared by incorporating the oil phase into the aqueous phase under high mechanical agitation. Due to the lower density of the dispersed phase, gravitational segregation compromised emulsion stability. To mitigate this issue, a concentrated emulsion with a dispersed phase concentration of 85% was achieved by the end of the preparation process. Dilution was performed in line during the flow experiments, mixing the concentrated emulsion with the stream of the continuous phase. Two emulsions with different drop sizes distributions were prepared by varying the rotor speeds. The stability of these emulsions was monitored, measuring the drop size distribution over time. Emulsions remain stable for at least 20 days. The experimental procedure involves several steps. In the water phase mobility test, the device was initially saturated with the continuous phase. The emulsion was then injected until a steady state pressure was reached. Following this, an additional injection of the aqueous phase was performed. In the oil displacement tests, an additional step was included. The device was first saturated with the oil phase. Water was then injected until the pressure reached a steady state and no further oil was mobilized within the porous media. Following this, an emulsion slug was injected and the additional injection of the aqueous phase was conducted. In radial flow tests, the capillary number was defined at the inlet of the porous medium. The experimental procedure included pressure drop measurements and real-time imaging. Following emulsion processing and data analysis were conducted. The emulsion injection model was designed to mix the concentrated emulsion with the stream of the continuous phase, achieving a dilute emulsion concentration of 595. So here I will present the first results from the linear flow. This is the linear micromodel. The linear geometry comprises a rectangular porous media. A distribution chamber was provided at each end of the porous medium to ensure uniform fluid dispersions across the inlet and outlet of the device, maintaining uniform pressure. Inlet and outlet ports facilitate the connection of the flow lines to the macromodel. And this macromodel had an absolute permeability of 100 Darcy. In emulsion flow, the transport of the dispersed phase significantly alters the dynamics at the pore level. In this sequence, we observe a small droplet marked in green moving smoothly through the medium, causing minimal resistance to flow. In contrast, a larger drop marked in red requires additional pressure to overcome capillary resistance and squeeze through the pore constrictions. If the drop is large enough, like the one marked in blue, it becomes trapped at the pore throat entrance. The critical pressure required to push a drop through a constriction depends on the drop diameter, the constriction size, and the interfacial tension, as described by the Engelbart equation. The critical pressure is reached as the front part of the drop begins to deform. Continuous pressure from the surrounding fluid increases the surface area of the drop, stretching it from a spherical to a cylindrical shape. As the front part of the drop moves out of the constriction, capillary pressure decreases, reaching its minimum when both ends of the drops are equal in size across the constriction. Beyond this point, the capillary force reverses direction, pulling the drop out of the channel and decreasing fluid pressure. The following sequences show how drops move through pore constrictions due to local pressure changes. In the first sequence, a large drop, marked in red, reaches the entrance of a constriction, raising the local pressure before quickly squeezing through the narrow passage. A smaller drop, marked in green, flowing closely behind, diverges at the junction, choosing a path with less resistance. Concurrently, the blue-marked drop experiences an increase in pressure and squeezes through an adjacent road, colliding with another drop at the outlet. In the following sequence, the large drop exits the pore throat and flows toward the next constriction, where fluid velocity increases due to a narrow gap. The change in velocity creates a pressure difference that pulls the drop through the constriction. And in the final sequence, the large drop reaches another pore throat and becomes trapped, causing pressure to build up. Once the pressure surpasses capillary resistance, the drop is squeezed through the pore throat, redirecting the flow to the mainstream. This is evident as the small green drop rejoins the primary path. The drop experiences local pressure changes as they flow along the channels. When squeezing through narrow constrictions, as shown in sequence 2, the drop experienced rapid pressure buildup due to the flow of the continuous phase being forced through small gaps. Thus far, we have analyzed the individual mechanisms of drops flowing in confined channels. When flowing through porous media, They create small flow perturbations that affect neighboring drops. Although decaying with distance, these perturbations affect local velocities, causing drops to change their trajectories as they flow through the channels. The video illustrates drops changing their paths as they navigate through the pore network. Small drops move smoothly through the channels, following the pressure gradients and avoiding tortuous paths. In contrast, larger drops alter their paths when encountering obstacles, like trapped drops or narrow constrictions, resulting in more tortuous paths. This dynamic process modifies the local flow field and allows previously trapped drops to re-enter the flow stream, intermittently changing the flow paths. The red hours in the images indicate different paths taken by the drops within a 5-second window. This video illustrates the initial stage of emotion injection. Upon entering the pore network, drops may either become trapped in narrow constrictions or move independently along straight paths, depending on their size relative to the constrictions. As more drops enter the medium, they locally reduce the network conductance, leading to interactions between droplets. With droplets moving closer together, the likelihood of jams forming increases. As the flow progresses, the drop density rises in the pore network, with jams continuously forming and disrupting. These dynamics create new flow paths, evident in the alternating flow patterns within the medium, shown by the red boxes. So we first examined the effect of the small drop emotion on flow behavior in the water phase mobility test. The inlet pressure rises until it reaches a steady state during the emotion injection, and then falls during the second water slug injection. The evolution of the injection pressure during the sequential flow of water, emotion, and water at the lowest flow rate explored, which in this case was 2 × 10⁻⁵. So during the first water slug, the injection pressure is constant and approximately 0.02 psi. During emotion injection, marked as the green region in the plot, the pressure starts to increase after approximately 2 pore volumes of injected emotion. The injection pressure increases until stabilizing at approximately 0.12 psi. After the injection of the second water slug, the inlet pressure drops to approximately 0.09 psi. In the early stages of emotion injection, as we can see in figure A, there are not enough large drops inside the pore space to cause an appreciable reduction in the flow mobility. As time evolves, more drops are captured in the pore throats, which leads to higher injection pressures, which is shown in figures B and C. At the end of emotion injection, the number of blocked pore throats is very high. The second leg of water can remove some of the drops that were blocking pore throats. We can see it in image D. But the number of blocked paths is still high, which explains the relatively high pressure difference at the end of the second water slug. The evolution of the injection pressure was also evaluated at the highest flow rate explored, which represents a capillary number of 6 × 10⁻⁴. And it exhibits a similar behavior, but with higher pressure values, as expected. The relative increase in injection pressure associated with emotion slug is less pronounced at high capillary numbers, as we can see by the images. The higher pressure difference in the flow is sufficient to overcome the capillary pressure, allowing a larger number of drops to pass through the pore throats. Consequently, the number of trapped drops is significantly lower compared to what we observed at the low capillary numbers. The water phase mobility test conducted with the large drop emotions demonstrated a similar behavior to that observed for the small drop. Because of the larger drops, pore blocking is stronger and a higher pressure gradient is needed to drive the drops through a pore throat, leading to a larger number of trapped drops. As a direct consequence, the observed injection pressures are higher. It is important to note that even after flow stabilization at the end of emulsion injection, the pressure value oscillates due to the dynamics of pore drop capture and release at different pore throats, which randomly alter the free flow paths. The dashed red arrows at the left image indicate the initial flow paths. Over time, the blue marked drops are mobilized and swept away, creating new flow paths, as shown by the solid red lines. Drops marked in green appear to restrain the flow, causing smaller drops to accumulate near the pore throat's entrance. With the establishment of the new flow path, the flow dynamics change, allowing the smaller drops to move past previously trapped drops. The mobility reduction associated with drop capture in pore throats can be quantified using the resistance factor. This factor is defined as the ratio of the steady state pressure difference at the end of the emulsion injection to that at the end of the first water injection. The resistance factor for both small and large drops falls with the capillary number, meaning that the mobility reduction is weaker as the capillary number rises. At low capillary numbers, the capillary pressure is relatively high compared to the flow pressure drop, and more emulsion drops are captured in the pore throats. As the capillary number rises, the number of drop captures is reduced, and the mobility reduction is not as strong. The value of the resistance factor becomes constant at capillary numbers higher than 3 × 10⁻⁴ for both emulsions tested. For the small drop emulsion and at the lowest capillary number explored, the resistance factor is approximately 6. The mobility of the aqueous phase containing dispersed drops is 1/6 of the water mobility. At the highest capillary number explored, which was 6 × 10⁻⁴, the resistance factor drops to 1.6. The resistance factor is higher for the large drop emulsions. Larger drops need to deform more as they flow to pore throats, requiring a higher pressure difference to overcome the capillary pressure, as indicated by the yellow dot. The results show that the intensity of the aqueous phase mobility reduction can be controlled by both capillary number and the drop size distribution. The residual resistance factor represents the ratio of the water mobility after the first and second water slugs. It quantifies the permanent mobility reduction. At the lower capillary number, the permanent damage is strong with a residual factor close to 10 and 5.5 for the large and small drop systems. As expected, the residual resistance factor is higher for the larger drops, since it is harder to displace large drops when compared to small ones. As the capillary number increases, the pressure difference of the flow becomes stronger relative to the capillary pressure, and more drops are displaced during the second water injection, leading to much lower values of the residual resistance factor. At the highest capillary number explored, the residual resistance factor drops to approximately 1.5 for both systems, large and drop systems. The permanent mobility reduction is directly associated with the extent of pore blocking by emulsion droplets. Now I will talk about the results from the radial flow. So the radial macro model consists of a circular porous media surrounded by an exit channel designed for uniform fluid drainage. The inlet port is placed at the center of the device, and 8 outlet ports are evenly spaced around the circular exits. In this case, the absolute permeability of the porous media was 13 Darcy. In radial flow, the cross-sectional pore area expands with increasing radius, causing the flow velocity to decrease as the fluid moves away from the injection point. The velocity is high near the injection point where we see marked in red, and decreases rapidly with distance from it. The pressure gradient is also not uniform along the radial direction, being significantly higher closer to the central inlet. Radial flow exhibits a pressure gradient extending outward in all directions from the injection point. In such configurations, tortuosity increases as flow deviates from the orientation of the posts, requiring the fluid to navigate around them to reach the outlet. We investigated the effect of a small drop in motion on radial flow at a low capillary number, 6 × 10⁻⁴. During the first water slug, the injection pressure remained constant at approximately 0.17 psi. Emotion injection, marked as the yellow region in the plot, lasted 15 pore volumes, causing the pressure to increase slowly. With continuous injection of emotion, a steady state pressure was achieved after 8 pore volumes, stabilizing at 0.5 psi. Emotion injection continued for an additional 7 pore volumes, after which the aqueous phase injection resumed for another 15 pore volumes, reducing the pressure to 0.44 psi. The distribution of drops after emotion injection shows a significant number of drops trapped within the medium, even far from the inlet. This suggests that the viscous pressure was sufficient to drive these drops close to the boundary. At the end of the test, the saturation of the dispersed phase decreased from 47 to 40%, indicating the mobilization of drops following the second water injection. This result is consistent with the pressure difference measurement, which dropped by 12% after the second water slug, decreasing from 0.5 to 0.44 psi. This video shows drops flowing from the bottom left to the upper right direction. The drops must maneuver past the post to traverse the medium. The intermittent change in flow path results in pressure oscillation, as we just saw at the previous test. In radial flow, fluid is expected to flow through low tortuosity paths. These paths are characterized by posts aligned with the pressure gradient. As drops accumulate within these paths, they locally reduce the network conductance, causing upstream drops to flow around the post through zigzagging paths. This results in recurring patterns emerging from the random distribution of constrictions within the grid. This pattern is replicated throughout the medium. In this image, the drops are represented in white, and we can see that the blocked regions are oriented in the X and Y directions, suggesting that the drops initially followed the low tortuosity paths before becoming trapped. Following the low capillary number test, we investigated the flow behavior of the small drop system at a higher capillary number, in this case 3 × 10⁻�3. The behavior was in line with the results from the linear flow tests at high capillary numbers. During the initial water injection, the pressure remained constant at approximately 0.81 psi. Upon emotion injection, the pressure increased until stabilizing at a steady state value of 1.19 psi. This pressure difference was maintained even after the injection of an additional 7 pore volumes of the continuous phase. During the second water flooding, smaller drops were flushed out of the medium, while larger drops remained trapped in the constrictions due to insufficient viscous pressure to drive them through. Although these small-scale events were visible at the pore scale, they were not reflected in the macroscopic pressure behavior, which remained steady at 1.19 psi. This indicates that in high capillary number flows, viscous forces vastly outweighed capillary resistance and govern the flow dynamics. Additionally, we know that at higher capillary numbers, the drops flow in the X and Y directions and avoid flowing through high tortuosity paths. Emulsion flooding was further conducted to investigate the dynamics of oil displacement by oil and water emulsions in radial flow. Initially, the continuous phase free of oil droplets was injected into the oil-saturated medium. As the continuous phase displaced the oil, the pressure dropped from 0.35 psi to 0.22 psi, achieving a recovery of 79% of the original oil in place. After injecting 65 per volumes of the continuous phase, the introduction of 1 per volume of dilute emulsion caused the pressure to increase from 0.22 to 0.30 psi without reaching a steady state. Finally, an additional injection of 30 per volumes of the continuous phase brought the total recovery to 84%. As previously discussed, in radial flow, the flow velocity decreases as the fluid moves away from the injection point. The pressure gradient extends outwards in all directions from the injection points. Near the inlet, viscous forces are more pronounced compared to those of the boundary. This happens because in radial flows, the velocity depends on the radius. And as the fluid moves away from the injection point, capillary forces become increasingly significant. With fewer droplets within the median, interactions become concentrated in a smaller area, causing localized pressure perturbations. These perturbations destabilize fluid dynamics, leading to the opening of new flow paths and facilitating the mobilization of trapped oil. In this figure, the aqueous phase is shown in blue, the oleic phase is shown in yellow, and the dispersed phase shown in magenta. Emulsion drops are primarily trapped near the inlet region, while the residual oil is scattered throughout the medium in the form of oil ganglia. The oleic phase saturation before and after emulsion injection is showed in this image. After being displaced by the aqueous phase, oil appeared scattered throughout the medium, accumulating near the outlet channel. At this point, the remaining oil within the pore space was immobile, with no changes in the aqueous phase flow paths. During emulsion injection, the flow equilibrium was disrupted, with drops causing local pressure perturbations, altering the flow dynamics near the injection point. As a result, a distinct clear region around the inlet emerged, indicating the radial displacement of initially trapped oil towards the outlet. The oleic phase saturation decreased from 21 to 16% after emulsion injection. While displacing the initial oil saturating the porous media, the aqueous phase exhibited a homogeneous distribution across the pore space. As emulsion injection begins, the aqueous phase becomes predominantly mobilized near the inlet. The areas previously occupied by the aqueous phase are now filled with emulsion droplets, as shown in the right image by the drops colored in magenta. The difference in saturation of the first and second water injection is subtle, rising from 79 to 80%. Despite this slight difference in saturation, the additional recovery of 23% of oil confirms the diversion of the aqueous phase to adjacent channels, improving the macroscopic sweep efficiency. This is corroborated by the pressure data, which shows an increase from 0.22 psi after the first water injection to 0.32 psi during the second water injection, indicating a permanent reduction in the mobility of the aqueous phase. As the drop enters the pore space, they spread gradually from the inlet, advancing in a regular circular front. Due to the limited amount of emulsion injected, in this case 1 per volume, the drops become concentrated near the inlet. Following emulsion injection, the aqueous phase drives the drops deeper into the porous media until capillary forces prevent further movements. The behavior of the capillary number as a function of the radius. The behavior of the capillary number is a function of the radius. The capillary number is higher near the inlet and decreases as the fluid moves toward the outlet. During the second water injection, the viscous pressure displaces the drops until the capillary forces hinder their movement at approximately 9.5 millimeters away from the injection point, marked by the red circle. This radius corresponds to a critical capillary number, which in this test was 2 times 10 to the minus 5. The radius represents the critical capillary number where capillary forces dominate, thereby controlling the movement of emulsion drops. The trapping of drops occur below this threshold value. So as final remarks from this work, we can highlight some points. At low capillary numbers, the mobility reduction is significant and highly dependent on the drop size distribution. Drops are retained in the porous media through mechanisms such as straining and bridging at low capillary numbers. When we increase these capillary numbers, the number of trapped drops decreases, leading to weaker mobility reduction. Drops are also captured by straining due to the high pressure difference, with smaller drops being flushed out of the porous medium. The second water flooding is ineffective at mobilizing a substantial number of drops after emulsion injection. The capture and release dynamics of the drops are primarily observed during emulsion injection. In radial flow, drops block the port roads if the local capillary number is below the critical value. The region of the flow affected by emulsion injection can be adjusted by controlling the critical capillary numbers for drop retention. And macrofluidic techniques allow for the correlation of the pore scale phenomena to the macroscopic flow behavior. This research was developed in the Laboratory of Microhydrodynamics and Flowing Porous Media at PUC-Rio. I would like to acknowledge the financial support from CAPES, Repsol Sinopec Brazil, Shell, and the Brazilian National Petroleum Agency. Thank you.
Thank you, Clarice, for your presentation. I'll start